So today we are going to discuss coverings, coverings over Lie groups. Can you say to me frankly, or I'm not going to be this frank, do you know what a covering is? I'm not asking, no, you should not reply to this question. For some of you, I know pretty well that you know this. So I will pretend that this notion is absolutely new for you. But if it is, certainly maybe you may somehow maybe will not be satisfied with this. So, first of all, a covering. Let me remind you a definition. We have two topological spaces and a continuous map of one of them and another one, P. P because it's projection. These two spaces, at the moment I assume that they are arbitrary in topological sense. There will be manifolds later on. And the only thing I need to assume that both path connected. This is my only requirement at the moment. So again, if you have questions, topology is not precisely a prerequisite, so you ask, and in 90% cases I maybe will be able to answer immediately. In the remaining 10% I will answer after the class. So we have this map, and it is called a covering, or sometimes people say that Y is a covering over X. Over because of this vertical direction of P. If the following holds, every point X in X has a neighborhood U, says that the inverse image of this neighborhood with respect to this projection, to this map P, is a disjoint union of sets, so that each of them is mapped by P homeomorphically onto U. So you can say, maybe it is not sounds very formal, that the inverse image is the union of a certain amount of copies of U, and they disjoint. This is the definition, and there exists a textbook example of this. This is a covering straight line covers a circle. A picture which is similar to that is this. So you present a straight line, such a helix, and the projection is vertical. Or you can say this map in coordinates, say this. Point X in the line. This example is not very interesting, but it is an example. There are other examples, which I will not discuss right now, but in topology, I can say that more or less everything is known about coverings. There are strong classification theorems, which I will not touch here. And let me first mention the first technical result regarding coverings. If we take, so again it is X, it is Y, take an arbitrary point x0 in X, take one of its inverse images, so point y0, which is mapped onto x0 by P, and an arbitrary path here, which begins at x0 and ends wherever it wants. Then there exists a unique path in Y which starts at the point y0 and is projected on the given path. So this unique lifting. And the theorem comes with homotopy invariance property. That is, if you vary this path continuously, then the lifting path also with the same starting point also varies continuously. In particular, if you have two paths in X with the same endpoint, and this deformation, homotopy as topologists say, preserves the endpoints, then the lifting path have to end also at the same point. Because what? When I lift it, then this point, when I lift, this point is lifted into some point which is projected onto it. But the inverse image of this projection is discrete. Is seen from this definition, right? So actually it cannot move if we impose the condition that it is projected onto this point. So this is the main technical property. I said technical because by itself it may be not very interesting, but actually almost everything regarding coverings follows from this lemma without, I can say, without any additional work. Now, why do we need this construction, this notion? This is because of the following thing. Suppose that we have not some mysterious space X, but rather a Lie group G. It is a manifold. I suppose it's connected. Otherwise, I cannot apply the theory here. And suppose that by this or that reason, it has a covering, some covering. So some other manifold, also connected, with a projection which satisfies the properties which I mentioned. Okay? Okay. Then, you know, G tilde, in a very natural way, also is a Lie group. Now let me make it more precise. So G is a Lie group. As such, it has the identity element, right? The inverse image of this identity element consists of, this is some subset of G tilde, and I choose one. So this is E, and I choose E tilde, which is projected onto E. This choice is not unique, but I make this choice. As soon as I do it, I can say that G tilde has a unique Lie group structure, a very much unique Lie group structure, such that E tilde is the identity element, and P is a homomorphism. By the way, the word homomorphism, certainly know it, but in this theory everything should be extended by the name of Lie. Lie homomorphism, the same as homomorphism. We just suppose that we have two Lie groups, a homomorphism of one of them and another one, which is also a smooth map between manifolds. That's all. So I say homomorphism, it will be automatically a Lie homomorphism. I didn't say this. But a covering over a manifold, Lie group or not, is also a manifold. By very obvious reason. Neighborhoods of points are the same in G and G tilde, right? So it is a manifold. If G is a smooth manifold, G tilde will be a smooth manifold. It is all obvious, and projection P is a local diffeomorphism. So it diffeomorphically maps a point, a neighborhood of point in G tilde in the in the some open set in G. It is all nothing. But I say more. I say that actually G tilde has a natural Lie group structure, and let me explain to you how it appears. So now I'm going to give you an explanation which is actually wrong. And you will altogether say to me that it is wrong by this or that reason. So, how to, a group, if you don't know, has multiplication. So we need to define multiplication in G tilde. This is my picture. It is E tilde. And two elements, well, I can write tilde just to make this picture more convincing. And I'm interested, what is G tilde times H tilde? I do the following. I take the projection of all this into G. Then I choose paths. You remember my both spaces actually are path connected. This is path connected, so there are paths. I choose them. And also project them. Path actually is a parameterized curve. So if we fix, so this path is, say, S, this is S1, S2. This is S1 of T, this is S2 of T, and this is a group. So I can take the product of these two. And you know, I will get some path. It ends at G times H, obviously, because the whole path is done by the product duration. Then I take this path and lift it, using my lifting property. Very interesting. And I say that this is, by definition, G tilde, H tilde. Colin, I expected that he will be not satisfied. So Colin, you know, but he's always not satisfied. So somebody else. Do you think it's okay? This definition. You know, your mathematical experience should show that something is wrong here simply because the construction contains an arbitrary choice. And we need somehow to be sure that nothing depends on this arbitrary choice, right? These two paths, say this path, we can replace it by some other path. Then projection also will be different. And who knows? Certainly, yes, what Colin said. We have some hope that, suppose that, I didn't say this, but suppose that I said that the space G tilde is simply connected. The word simply connected may be known to you from multivariable calculus. I don't know how you, certainly you use this notion in calculus, I don't know how you call it there. But simply connected means that every two paths joining two points are homotopic to each other. So we can have a homotopy which preserves the endpoints. This is called simply connected. Do you remember when and how you use this in multivariable calculus? You know, for example, you have two functions p and q, and I don't know whether you call it the Tho's differential form, p dx plus q dy, in the plane. And if some partial derivatives are equal to each other, this gives you a necessary condition for this form being differential function, potential function. You need that dp over dy is equal to dq over dx, right? It is necessary. It is sufficient. Yes and no. It is sufficient if the domain in which you consider this function is precisely what I said, simply connected. Otherwise, it is very possible. For example, it's very possible to find functions p and q in the plane with one point deleted, so that dp over dy will be equal to dq over dx, yes. But still, there are no function. Well, maybe you can say no univariate function, but no function. No function of two variables such that p is the derivative of the function over dx and q is the derivative of the function over dy. I don't need this, or at least I can pretend that I don't need it. I say this only to convince you, and don't know how much I'm successful in that this notion is well known to you. Not only notion, notion after all you have definition, but the importance of it. So, if we assume that G tilde is simply connected, additional property, then these two paths will be homotopic. These two paths will be also homotopic, that's projection of homotopy. And the product path also will be replaced by a homotopic path. And as I said, when we lift homotopic path, then the endpoint of the lifted path will be the same. So it is okay. But what if, so what I did is important. I explained to you that this definition is, this is all well defined. If G tilde is simply connected, actually very important case. But still, I don't want to confine myself to this case. What if G tilde is not simply connected? What would you say, Dale? Will it kill all our hopes?
Double covering of a circle?
No, it's an example. Double covering of a circle, yes.
Pull it up to the universal cover, then project back down, maybe?
Yes, it is a possibility. I actually didn't think about it. Yes. Well, I wanted to describe here a different procedure, but if Colin suggests this, then yes, let us consider this. Universal cover. I said that the main technical theorem in the theory of coverings is this lifting path lemma. Actually, there is one more technical theorem, and I cannot judge which of them is more important. Existence. No existence result. To have classification, we need to have existence. Maybe no coverings at all, and we don't know, we simply don't see them. So the theorem I formulated precisely as Colin needs. If the space X, I return to my topological definition, is, well, you will not be satisfied with this, good enough. If the space X is not very bad, it's not nasty, then there exists a covering say that Y is simply connected. It's called universal covering, and I can easily explain why. Now, there are topologists like this a lot. We are not topologists here, but there exists a description of class of spaces for which this construction of universal covering exists. But let me say that if your space is a manifold, then it's okay. Every manifold has a universal cover, and it is constructed in a very explicit way. I will not do this construction here, but you actually also know this construction, maybe not from multivariable calculus, but at least from from complex analysis. If you take a analytic function, then you can extend it. You can do bigger and bigger set, and at some moment you come back and you discover that actually the function which you get on a set where this function also exists, the function will be different. It is very possible. And this actually is the geometry of this transition, is the construction of the universal cover. I will not say anything else about this. So there exists a universal cover. Why universal? I don't want to discuss why it exists. It's why universal. First of all, it is absolutely unique. If we have the same space X, well, I can write just one X to save some chalk. And two universal covers. Then what? Then I want to construct a homeomorphism between these two spaces, which makes this, both maps make this, as algebraists say, diagram commutative. How to do it? So this is X, this is Y1, this is Y2. Actually, I need to fix one more thing. Some point here, and point here and here, which are projected into this point. Otherwise, this will not be unique, still exists. So we have a point here, and point here. And my map certainly will take this point into this point. And now I have some other point. What to do? I take a path, I project it into X, and then I lift it here, right? And then I say that this is my map. Take this point and this point, right? And actually, this doesn't depend on this path, because by the same reason, this space is simply connected. Any other path would be homotopic to it. So this map is well defined. It's very clear that the map is unique, because this path must go to this path. Projection, lifting. So there exists a unique map of Y1 into Y2, which respects this choice of points and makes the diagram commutative. Certainly the same in the opposite direction. And the uniqueness shows that the map Y1 into Y1 will be which is the composition of two maps, will be the identity. So there is a thing. So there exists a unique universal cover. Exists, well, you have to believe the proof takes 10 minutes, but I will not spend the 10 minutes. So, if we have an arbitrary, no one, the second will appear, a very arbitrary covering, not universal. But these spaces both have universal coverings, right? This space has a universal covering. And the composition will be the universal covering for this, right? Yes. So I can say the universal covering because it's unique. The universal covering of a manifold of a good topological space is called universal simply because it covers any other covering. It's above everything. And then we can apply what Colin said, that for the universal covering, this Lie group structure, this multiplication is well defined, and then we can project it into G tilde. Just take 2 points here, take their inverse images. Yes. So this G tilde, now I return to an arbitrary covering, is a Lie group. In my notes, there, another approach is presented. You can look through it. How to define actually the multiplication G tilde, also the inversion, the same way, also by lifting. And you have a Lie group structure in G tilde. Examples. There are examples. A very stupid example, it is what we already have. A straight line covers a circle. A circle is a Lie group. We discussed this. Hence, a straight line requires a structure of a Lie group. Not a big deal. R is a Lie group without this construction. And the Lie group structure which we obtained in this way in R will be the same which children study in elementary schools. Usual addition of numbers. Do you know any other examples? Can you imagine other examples of Lie groups which may have coverings?
One example. S1 cross S1.
It is, yes, certainly you can take products. It is not very interesting. Something more interesting. If you really want to play this game, to pretend that you don't know this, the classification of coverings. What I can say that, for example, the group SON. The group SON has a covering, as people say, twofold covering. Twofold, it means that every point has, the inverse image of every point consists of 2 points. Twofold covering of SON becomes a Lie group. Do you know how this Lie group is called? You know.
Spin group.
Yes, spinor group, spin notation. The group, you know, when people speak about Lie groups, they also have an example. Not R, no. You may know this. Suppose that we have some Lie group. For example, let us take SL2R. SL2R, by the way, has a universal cover. A very stupid group. This will give us a funny example later. Now I don't have the problem to which this example. You will not simply see why it is so funny. Yes, so there are, there is such a possibility that a Lie group has a covering over this Lie group, maybe universal, maybe not. The spin group is universal if n is at least 3. Some groups are simply connected. Simply connected spaces, they do not have any coverings because the identity map is a universal covering. Yes. Now, I want to make just one very small, very funny remark. Suppose that we have a Lie group G. And some covering group, not necessarily universal, G tilde. And this is a homomorphism. Homomorphism, believe me, have kernels. What can I say about this kernel? Kernels in general are subgroups, right? Wonderful. So this is a subgroup of G tilde. Not just a subgroup. A kernel of any homomorphism is a normal subgroup. Thank you. So this is a normal subgroup. What about topology? Absolutely discrete, because for any covering, Lie groups are not. The inverse image of every point is a discrete set. So it has two properties. Normal, discrete, but this is not all, because the combination of these two properties gives a very interesting thing. Know what? It is normal, it is discrete, but also it is, please say, closed, discrete. abelian. It is not all, but it is abelian. It is central. Do you know what central subgroup is? This means that every element of the subgroup commutes with every element of the whole group. So this group is central. And this is not just a property of this group. For every connected Lie group, a discrete normal subgroup is central. And I want to say that this is obvious. So G is a connected Lie group. Gamma is a discrete and normal. What does it mean? Well, you remember your algebra. This means that if you take a gamma in gamma and G in G, then G inverse gamma G again belongs to gamma, right? But when gamma is fixed, this depends continuously on G. And what do you think, my friends, of a function depending continuous and taking values in a discrete set? I personally think this function should be constant, right? If G inverse, if you vary G, then G inverse gamma G should be varied, right? But still, since gamma is normal, it stays within gamma. It cannot go anywhere. Certainly, it's important that G is connected, but we do assume this. So this group is central. Dale, yes, it is abelian, but much more than that. Much more than that. So if we look at this problem from the opposite side, we consider other G tilde, some Lie group, and we want to know whether it covers some other group. We need to look at what? At its center. We want to know all discrete central subgroups, right? In G and G tilde. We find it. We do the quotient. The quotient over Lie subgroup certainly will be discrete subgroup will be also a Lie group. Can you imagine discrete central subgroups in Lie groups? As I said to you, when people speak of Lie groups, usually consider, for example, the group SL2R. The group SL2R, can you detect a non-trivial central in it? You can. Take the identity, every subgroup should contain identity, and take negative identity. Also an element of SL2R, right? 1 minus 1 times minus 1 equals 1, believe me. So this group SL2R has a normal subgroup, central subgroup of 2 elements. It is very much abelian, but also central. What do you think of the quotient? You can know the notation and the name. It's denoted as PSL2R, and it's called the projective group. When you identify a matrix, and mine is the same matrix in SL2R, you will still have Lie group. It's called PSL2R, very important actually. Now, I have 5 more minutes, and I don't want to spend them on one small, very short. Ah, yes, thank you. You know, yes, then I have a lot of time. Good. Then I will say something important to you. So again, suppose that we have a Lie group G and a subgroup H. Well, not normal, not discrete, just a Lie subgroup. Submanifold. Then I'm going to take the quotient, G over H, right? What do you think of this quotient? I can say what I think of this quotient, but maybe you have some impression what it is. This quotient actually, certainly if H is not normal, it will not be a group. This is everybody knows. But still it preserves a manifold structure. And this requires, especially in the case when H is not compact. Suppose that G and H both not compact. If H is not compact, then this requires some work, which is done in my notes, 1/3 page. I will not do this now. I will not need this. But there exists a notion which is cherished in many parts of mathematics, which is called homogeneous space. Have you ever heard these words? A homogeneous space. I give you a definition which is slightly more general than which is normally used. We have a manifold, M. And we have a Lie group which acts on this manifold. You know what is an action of a group on a set? Good. Certainly I suppose that this action is very much smooth. That is, the map of G cross M into M is a smooth map. We have this action, and then we assume also this action is transitive. And then M is called a homogeneous space. Homogeneous space because there exists a transitive action of a Lie group. Usually in textbooks, this term is applied to the case when H is compact. G usually also compact. So when I said that the quotient of G over gamma is a Lie group, this has a generalization. A quotient of G over over any Lie subgroup is very certainly is a manifold. If this subgroup is normal, it becomes a group, then hence a Lie group. And this can be applied not only to the case when the group over which you factorize is discrete. It's not necessary. When you describe the manifold structure on this coset space G over H, you need actually to do some work, which is done in my notes. I will not do it now because if I need homogeneous spaces at all, later it will not immediately. So now I want to turn to the next subject. And my next subject, the next section in my notes is called tangent vectors and tangent vector and vector fields. So this is what I'm going to consider now. Again, my question to you. When I use this term, I have a manifold. So manifold, I use it and you seem to accept it. If I use the word tangent vector, do you know what it is? So there are 1,000,001 definitions. The most convenient one, which I used last quarter in my course of differential topology, is the following. I identify a tangent vector with the operator of directional derivative, which means that a tangent vector have a manifold M and a point P in M. A tangent vector Xi is defined as a map of the space of all smooth functions on M into R.
Professor Fuchs?
Yes.
Your microphone.
Oh, my God. Thank you. But this will not affect probably because my microphone is here. So, a tangent vector is a map of C infinity M into R. Say that for every two functions P and F and G, M, they were at P. Xi of G is equal to Xi of F times G of P plus F of P times Xi of G. This is one of many possible definitions of a tangent vector, which is very convenient technically. And tangent vectors at a certain point to a manifold form a vector space. Its dimension is equal to the dimension of manifold, and there are coordinate presentations and so on and so on and so on. I don't need all this now. It is a tangent vector, a vector field. A vector field actually is what people usually mean by vector field. So we have a tangent vector at every point of the manifold, or some domain maybe, if it is defined in some domain, which should depend sort of smoothly on the point. It is again more convenient to define a vector field X simply as a derivation in the ring of functions. That is, X is a vector field. X is a map of C infinity M into C infinity M. C infinity M is a ring of functions. And X of F G is equal just X of F times G, usual product rule. This is a vector field. I am not interested now in this theory of vectors and vector fields in full generality. Vector field can be defined actually as family of tangent vectors at all points of the manifolds. It is very easy to relate these to definitions. But what I want to say now is the following. We consider not just a manifold, we consider a Lie group. So G, let G be a Lie group. And I consider the space of tangent vectors to the group G at the identity element. To say that this space is important is to say nothing. This is the second important notion in the Lie theory. But at the moment you at least can pretend that you don't see it. T, E, G, actually we can consider tangent space at every point, at any other point. Actually one of many vector spaces which can be, which you can imagine arise in connection with G. Actually, this space, TG, has an important additional structure because it has a bilinear operation which is called commutator. It becomes a Lie algebra. And the main idea, technical idea of theory of Lie groups is that we mostly reduce all questions, including topological problems, related to a Lie group G to pure algebraic questions regarding this Lie algebra. And algebraic questions, in some sense, always easy to answer. Usually can be answered by some very formal constructions. I will not consider this structure now. I want to consider a different thing. First of all, as soon as we have a Lie group, we have three important family of self-diffeomorphisms. Lambda G left translation, lambda g of h is gh. A diffeomorphism of g onto itself. Rho g, right translation. Rho g of h is hg. Also, there exists a combination of these two maps, conjugation. Alpha g, g into g, alpha g of h is g inverse hg. You know, maybe it will be more convenient to you to write gh inverse. Yes, I prefer this. What can be said about these maps? First of all, lambda g and rho g are diffeomorphisms. They commute with each other. That is, if you take lambda g1 and rho g2, you can apply them in any order. Just multiply h on g1 from one side, on g2 from other side, and then nobody remembers which was the first. Diffeomorphisms. Certainly they are not homeomorphisms, because they take the identity into G. Now, the conjugation. This is an automorphism. It takes products into products and inverses into inverses in inverses. Well known. Immediate formulas show this. Also, I can say that if you consider the whole amount of maps lambda g, this can be regarded as the left action of G on itself. And then this words, every element of G defines some transformation in G, and certainly it is a group action. Rho G, the set of all rho G, is a right action of G onto itself. Alpha G is more than that. It is certainly also an action, but it is an action of G, left action, if I write in this order. Left action of G onto itself by automorphisms, which makes it very attractive. And if you wish, I can say that this is the most important action, but I say this only to state that I will not consider it now. It will be for our later exercises. And now I consider rho G and lambda G and rho G. There are such words in theory of Lie groups. Left invariant, right invariant. This is applied to many things. To vector fields, to differential forms. This means that we have an element of some set such that actually transformations of G can be applied to this set. Maybe set of vector fields, set of, well, many different opportunities. And left invariant, without any specification what I mean, simply linguistically means left invariant is something which is invariant with respect to all left translations. And right invariant, you can guess. Invariant with respect to all right translations. Now I want to say, this is the last thing I can say today, but it is again extremely important. Suppose that we have some element of this space, see? Just a tangent vector at E. What happens if I apply to this tangent vector all left translations, or maybe better to say differentials of left translations? So I take G, and this vector by left translation is translated into some tangent vector at G. And this is for every G. Right? What we get? We get a vector field. And this vector field is left invariant. which means that every left translation of the manifold takes this vector field into itself. I can say more. This will be my last word today. Every left invariant vector field is like this. Because if we have a vector field, then it has a value at E. If it's left invariant, then its values at all other points are obtained from this value by left translations. What can I add to this? So left invariant vector fields on G are in one-to-one correspond to elements of T and G. The same for right invariant vector fields, same construction, which uses right translations instead of left translations. And I thank you very much for your kind attention. See you the day of tomorrow.